Section 5.5 is titled The Real Zeros of a Polynomial Function, and sections 5.5 and 5.6 are both closely related to each other, so you'll notice they'll tie in a few of the concepts that we've already discussed in this chapter with regard to polynomial functions. Specifically talking about the zeros of a polynomial function, and the whole idea behind section 5.5 and section 5.6 is basically to figure out, okay, if we've got some polynomial function, whatever it is, how do we find the zeros of that function? What are some techniques? What are some ways we can look at that function and kind of study it and determine what the zeros of that function are? And it's something that is useful for a lot of things. When you look at applications of polynomial functions, we're not going to really specifically get into that much in what we're doing here. We're just looking at some techniques on how to find the zeros of the polynomial function. So section 5.5, the first thing we're going to do is we're going to look at what are called the remainder and factor theorems, and kind of set up one tool that we're going to use to help us find zeros. And then we've got really two things that we're going to use to help us find zeros, which is something really easily that will tell us how many or what the maximum number of zeros we could have for a polynomial function. Then also something called the rational zeros theorem, which is going to give us a nice list of potential zeros of a polynomial function. And then of course these last two objectives are just putting those to use, finding real zeros and also solving polynomial equations. So first let's talk about these two theorems, remainder and factor theorems. You don't really need to know just a ton about the remainder and factor theorems to specifically. I'll explain here in a second what the practical uses of the remainder and factor theorems are, but just to state them and say what they are. Say f is some polynomial function. If we have f of x and we divide it by x minus c, then the remainder is f of c. So if you had like x squared plus 2x plus, let's say, 1, and you divided that by some other polynomial, x minus 4, whatever the remainder of this division is, it's the same as if you were to plug this value right here. This is x minus c, so x minus 4, it's the same as f of 4. Okay, the remainder of that is. And it's kind of a weird thing, and again, not something we're specifically going to really use much. Kind of something that goes with that's the factor theorem. It says if f is a polynomial function, then x minus c is a factor of the function if and only if f of c is 0. Now that should make sense. When we say x minus c is a factor of f of x, then that means that it, in a sense, it divides evenly. Factors are pieces that can be multiplied together to get the function f of x. So if x minus c is a factor, then x minus c divides evenly into that function, which would mean, remember that we just said that that's the remainder, right? F of c is 0, remainder is 0. So that's the remainder and factor theorem. Now, how do we actually use those? Well, it's this second piece here, this x minus c is a factor if the remainder is 0. Okay, that's really what we're going to kind of use in this whole idea of trying to find these real zeros. And so that's this statement here in bold. If we divide a function by x minus c and the remainder is 0, then we know that x minus c is a factor, and also that c is a 0. And we'll get into that here in just a second. But let's practice dividing a little bit here. So let's find the remainder of the function f of x equals x cubed minus 4x squared minus 5 if we divide by x minus 3. Now we're going to use something called synthetic division to do this. Synthetic division is how we're going to determine if x minus c is a factor and what the remainder is. Okay, and so the way synthetic division works, you just kind of follow my lead here. Synthetic division is a shortcut method for division if we're dividing polynomials, and we can only divide polynomials using synthetic division if the divisor, that would be what we're dividing by, in this case x minus 3, is in the form where we have a single x and then plus or minus some single value. So x minus 3, we can do synthetic division. If that were x squared minus 3, we couldn't do synthetic division. If that were 2x minus 3, we couldn't do synthetic division. It has to be x plus or minus some constant value. Okay, so for the sake of what we're doing here, anytime we're checking this division, we can use synthetic division. They'll always be set up that way. So, what does that look like? Well, the first thing we're going to do, if we have x minus 3, we're going to take the opposite of what we have here. That's a minus 3. I'm going to put a positive 3. And then I'm going to draw an upside down division bar. Okay, the next thing I'm going to put is, you want to leave enough space for like 2 rows of numbers here. Okay, so the next thing I'm going to do is I'm going to put the coefficients of this polynomial on this top row here, starting with the highest power of x and stepping down. So in other words, this is going to be a 1x cubed. Okay, right here is my x cubed. My next column is going to be my x squared, and then my x, and then my constant. Okay, so my x squared, I've got a minus 4 x squared. For my x column, there's no x term up here, so I'm going to put a 0 placeholder, and then the constant, I have a minus 5. Okay, so that's the setup. So I'm now set up, ready to divide. And that's really the hardest part, is the setup. If you can get that set up, then the rest of this is pretty easy. The way it works is, first thing you do always is bring down the 1, and then you're going to multiply three and 1 to get 3 times 1 is 3. Okay, so bring down the 1, multiply, we get a 3. And then we're going to add this column here. So add negative 4 plus negative 3 is, sorry, negative 4 plus 3 is negative 1. Okay, so that's pretty much the process. You just keep doing that. Multiply 3 and negative 1, we get negative 3. If we then add, we get a negative 3. And then we just keep going. Multiply 3 and negative 3 to get negative 9. And then if we add those, we get a negative 14. Okay, so that's the process. Multiply, add, all the way across. This number right here is what we're looking for. Okay, that very last number in that last column is the remainder of that division. I know this looks like just a huge mess, but that right there is our remainder, that last number. So our remainder is negative 14. So we've answered example 1. We found the remainder. So the remainder is negative 14. Now, what does that tell us about x minus 3 for this polynomial? Well, x minus 3 is not a factor of that polynomial. Also, that tells us positive 3 is not a 0 of that polynomial. Did you follow that? We'll get into that more here in a little bit. Let's look at part B. We're going to have the same setup. We're dividing by x plus 2. So I'm going to start with the opposite of this, which is a minus 2. And then the same 1, negative 4, 0, negative 5, because we're dividing into this same polynomial here. Okay, so just working this down, bring down the 1, negative 2 times 1 is negative 2. If we add negative 4 and negative 2, we get negative 6. Multiply again, negative 2 and negative 6 is 12. If we add that, we get 12. Negative 2 times 12 is negative 24. and we get negative 29. And again, that is our remainder. Okay. So that's that. To answer the question, remainder is negative 29. Now, example 2 says use the factor theorem to determine whether the function f of x is all that has the factor x minus 1 or x plus 3. So kind of the same question almost, but instead of asking about the remainder, we want to know, is x minus 1 a factor of this polynomial right here? So the way we do that is use this synthetic division. Okay, so here's a minus 1, so I'm going to put a positive 1. And then for my coefficients, starting with the highest power of x, that's 2x cubed. Okay, remember we're going to go in x cubed, x squared, x, and then the constant. Okay, so x squared, we got a minus 1, right? There's an understood 1 there, plus 2, minus 3. Okay, just taking those coefficients. And the synthetic division process, bring down the 2. 1 times 2 is 2. Add negative 1 and 2 to get 1. 1 times 1 is 1. 2 plus 1 is 3. 1 times 3 is 3. And if we add that, we get 0. Okay, now this is important. 0. What's special about 0? What does that tell us? Well, that means x minus 1, if the remainder is 0, that it divided evenly, right? Or we could also say if x minus 1 divides evenly, it's a factor of that function. So we could say x minus 1 is a factor of f of x, this whole polynomial up here. 2x cubed minus x squared plus 2x minus 3. We could actually do better than that also, and the question doesn't necessarily say to do this, but we can actually begin to factor that polynomial. Okay, here's something else synthetic division does for us. This is just a little bonus here, which we're going to do this more here in a minute, but I'll go ahead and show it to you. X minus 1 is a factor of that polynomial. So in other words, that function is the same as x minus 1 times something. The question is, what is that other piece right there? Well, we could get that from these numbers right here, 2, 1, 3. These other numbers at the bottom of our synthetic division, those are coefficients of a polynomial whose degree is 1 less than what we started with. Okay, we started with a third degree polynomial. So these right here, these are coefficients of a second degree polynomial. In other words, that's 2x squared plus 1x plus 3. And now you can see we're beginning to factor that polynomial using synthetic division. Okay, and that's we'll get into that more here in just a little bit. But if you understood what I did there and kind of grasp that, I mean, that's really it as far as this section goes. We'll add another piece to it here in a minute, but that's really the meat of what we're doing here, is finding those zeros and factoring those functions. Okay, and that problem right there was a good example of what we're going to be doing later on here in this section. So let's look at part B. We want to know if x plus 3 is a factor. So again, setting up the synthetic division, take the opposite of what's here, that's a minus 3. We're going to use the same coefficients, so that's a 2, negative 1, 2, negative 3. Okay, bring down the 2. Negative 3 times 2 is negative 6. If we add those, we get negative 7. Multiply there, that's a positive 21. Plus 2 is 23. Negative 3 times 23 is negative 39, plus negative 3 is negative 42. Negative 42, that's not 0. So x plus 3 is not a factor of that original polynomial f of x equals all this up here. So we're just looking for that 0 remainder. That's what we're trying to find. If that's not a 0 remainder, we know it's not a factor. Okay, here's another helpful piece of information. This is pretty simple. The maximum number of real zeros for a polynomial function is the same as its degree. So if we have a polynomial function, it can't have more zeros than its degree. Okay. Now think for a second why that's the case. Why can we not have more zeros than our degree? Well, think about if we have a 0, say we had a third degree polynomial with 4 zeros, okay? Let's just make it easy. Let's do 1, 2, 3, and 4. Okay. So a third degree polynomial with those zeros. Can we do that? Is that possible? What would that polynomial look like if we were to write it out? Okay, if we have 1, 2, 3, and 4 for zeros, don't we have x minus 1, x minus 2, x minus 3, and x minus 4 for my zeros? I'm sorry, for my factors. And what would the degree of that polynomial be? Don't we have x times x times x times x, which is x to the 4th? Okay, that's not a third degree polynomial, that's a 4th degree polynomial. So we can see that that doesn't really make sense. We said it was a third degree polynomial with those zeros, but it was actually 4th degree. And the reasoning behind this idea that your polynomial can't have more zeros than its degree is because the zeros really, they determine the degree, right? If we have 4 zeros, well then that means it's at least a 4th degree polynomial. Now, one thing I want you to notice also, though, is that it doesn't say that you will have as many zeros as your degree. It says that's the maximum number of real zeros you can have as your degree. So you could have a situation where you have like a third degree polynomial that only has 1 real zero. And if we chase that idea a little bit further, we end up getting into section 5.6, which delves into complex zeros and imaginary numbers, and we'll get there soon enough. But for now, just know that you can't have more real zeros than your degree. Okay, pretty simple.